So here, from the flatearth.ws website, it says an object falls down because of Earth's gravitational attraction. Well, first of all, that's wrong. There is no attraction. In mainstream consensus today, it's actually an object following a geodesic or following the bending of space-time. Not an attraction, just following a path, not attracted. But some denominations of flat Earth claim that an object falls down due to its density, not gravity. So then they've got a balance scale, 2 litres of water on one side, 1 litre of water on the other side. Same material, same atmosphere, same density, different mass, different volume. Yes, correct. By putting two objects of equal density and different mass against each other using a balance, it is easy to see that the object's density is not the reason it falls down. Right, but then you've changed the volume. So if you keep the density the same and you change the volume, then you're not measuring density difference, are you? You're measuring mass difference. So if you keep the density the same, which is like kgm3, then you keep 1m3, because obviously kgm3, so basically the mass per unit volume. So if you keep the unit volume the same, so if you keep the volume the same, and you keep the density the same, then they will both neither rise nor fall. The balance scale will not tip, because they will be the same density. However, if you put the same volume on again, but you use different densities, then the more dense one will go down and the less dense up. And this is just a balance scale. So obviously, it's just measuring. Well, it depends. It can measure both mass and density. Like I said, if you have the volume the same, then and the density the same, then obviously they will neither rise nor fall. So therefore, it's measuring the density and saying the density is the same. If you then increase the volume but keep the density the same, then obviously it's not measuring density anymore, it's measuring mass. If you have the same volume but different densities, then obviously the more dense one will go down and the less dense one up, because then you're measuring relative density. Well, not relative density, but one density relative to another on the balance scale. So obviously the more dense one will go down then if you keep the volume the same. So then you will be measuring density. So you can both measure density and mass depending on what you use it for. But if you're going to measure density, then you're going to have to keep the volume the same, because density is per unit volume. You're not keeping the volume the same, so therefore you're not measuring the density, am you? You're not measuring one more dense than another, or whether they're the same density, because you're not keeping the volume the same. So of course this is going to have more mass go down and less mass up, because the volume's not the same. So you say an object falls down due to gravity, but not its density. Okay, so basically you're saying this measures mass, and that more mass will go down. Except that's not the case, is it? For example, I can have a rock and I can have a cruise ship. I throw the rock into water, it has little mass compared to the cruise ship. The cruise ship floats. The little mass of rock sinks. Now what has the most mass? The cruise ship has the most mass, right? And the rock has the littlest mass out of the two. Yet the cruise ship floats and the rock sinks. Yet the cruise ship has more mass than the rock. Yet the cruise ship didn't go down, but the rock did. The reason the cruise ship didn't go down is because it was less dense than the water. The reason the rock went down is because it's more dense than the water. Again, density proven right there.
So they obviously picked that this one's heavier. You can check it if you want. You can have a balance out. And so since it's heavier, it's going to sink. And since this one's lighter, it's going to float. Oh, isn't that wonderful? Okay. Well, all right. But when I take them out, actually, I usually have them a little closer together. If I fumble enough, and the kids are used to me fumbling, sometimes on purpose and sometimes accidentally, if I fumble and I drop it, then we've got a problem here. Well, if that happened, what happens if I take this piece of candle and drop it in the other beaker, and it sinks? So now the heavy one is floating, and the light one has sunk. All right. What's happening here? And I wait. And somebody will say something, and somebody will say something else. You tricked us. They're not from the same piece of candle. I pull them out and have a student test them. The believe it or not, the last thing they want to tell me is that they are different liquids. And that is the case. And the point I'm trying to make to them is that it's not the difference in the candles and that makes something float or sink. It's not the difference in the liquids that'll make something float or sink. It's the difference in the density of the floating object and the liquid that you put it into. It's not that this candle is heavier than the other one. It's not that it's more or less dense than the other. It's that the candle, and both of them, are less dense than the liquid they're floating in. And in this case, they're more dense than the liquid they're floating in. So we're comparing the object to the liquid and not to each other.
AKA relative density.